Finally, let's now talk about the composite design pattern. In some way, you have already learned about most of it when you criticize the previous two design attempts before we talk about multiple inheritance. So now, for the composite design pattern, let me just highlight the difference we are trying to make over here in the final design. Let's now take a look. So remember, we criticized about the very first design attempt being a lack of cohesion, and the second design being lack of the single choice principle, right? So now let's see why these two principles can now be both satisfied by the ultimate composite design pattern. Let's see. Again, let me very quick recap. You can see we got the equipments over here. This is one category of the equipment. So any direct descendants classes of equipment should be basic components. And also we introduced this intermediate kind of equipment called composite. And then, for example, cabinets, chassis, and also bus. And so these are the composite equipments, right? So these are the two kinds. And now, and don't forget, we also have this interesting arrow over here to say children over here. So this is a client-supply relation, meaning that the composite equipment is going to contain a child list. Every one of them is going to be of type equipments over here, right? We can see the dot dot over here is going to be of type equipments, okay? So that's something we discussed in detail already. And now notice the interesting bit over here. So now we are using multiple inheritance. You can see composite equipments over here is a subclass of both equipments over here. This is one parent class, and also the composite class. Okay, so now let's talk about both design principle, but we do have multiple inheritance because it's supported by our design language. So let's see, first of all, cohesion. Is cohesion satisfying? The answer is yes, because now for the basic components over here, for example, over here, they do not inherit any features that's related to, for example, children and also add child. They're only inherited to the composite equipments, but not the disk and also video. Meaning that, so now, if you look at this particular line, that compiles for the very first design attempt we made. So now, if you say card, which will be of type video card, does it support add child? No, it does not. It only inherits whatever that's in the equipments, which does not include the children and also add child. So this will not compile. So this will not compile simply because we don't want to create any system that's out of the reality sense. Okay, so cohesion is good. Okay, it's a very quick explanation. So what about single choice principle? Let's talk about single choice principle. The reason that the second design attempt didn't satisfy single choice principle was, so for the composite that used to be containing the children and also the add child, right? Remember, and we said that if you want to create just another cluster solving a similar design problem, you will have to duplicate basically, for example, furniture composite with also children and add child. But now what we're doing is we're factoring out that common code about manipulating the child list or any children list in this particular generic class called composite. You can see the T over here. You can see the T here is generic, which means it can be instantiated by whatever class that's needed. For example, T can be instantiated by equipment, or T can be instantiated by furniture, which I'll show you in just one in a moment. Okay, so this part here tells you the single choice principle is also satisfying, because now later on, whenever you want to create any additional cluster, for example, there's a cluster over here, you also got some composite class. All you got to do is make sure that class also inherits from this particular composite class. That's what you got to make sure. So now you're really reusing the code that's in a single place. So single choice principle is satisfying. All right. I have two questions for you. Well, the first one, just observation. Let's now relate a little bit to the subcontracting that we talked about. Okay, so now you can see over here, so here children is simply just a list, and we simply don't have any constraint about what should be the size of the children's list, right, in the composite level. It does actually make sense, because in the composite, which might be reused by many other different clusters, so now we may not actually want to restrict the size of the children list. But let's say, for example, what if I want to say, for my particular composite equipment, let's say especially for chassis, let's say each chassis shouldn't consist of more than 10 components inside. So now how do I impose that constraint? Well, it seems to be I can accumulate the invariant, right? You can think about it would be as if over here I said invariance simply just true, because I simply don't put any constraint, right? So it's as if invariance actually true. at the composite class level. But now in the cabinet, let's say in the chassis class over here, I can just declare invariance over here. And then over here, I can simply say, for example, the children, the list, let's say should be less than or equal to 10. So at the runtime, what's going to be checked? At the runtime, it's going to be the combination, the conjunction of true and also this particular predicate, which will be equivalent to just this predicate. So that means dynamically, if the type of the equipment is simply chassis, in that case, the count for the children should be less than or equal to 10, right? That's the first thing I would like to mention about linking to the subcontracting lecture that we spoke about previously. Second thing I would like to talk about, this is more like a question for you, okay? I have a question for you. You can see this interesting arrow over here, children, is actually pointing to just the equipments, meaning that this dot dot over here is simply just equipments, right? Can we alternatively do the following arrow? For example, I want to do the following arrow. I want to say, from here, I want to draw an arrow like this, okay? You know what? Let me try not to do any overlap. Let's say this particular arrow. So this is my proposed client-supply relation over here. So now, can I say the following? So now the green one is going to be children. And then it's going to be the list of dot dot. So now the dot dot over here is now referring to the composite. Can I have this particular alternative design over here? So this is my question. Okay, think about it, and then if you got any concern about it, you can raise this up maybe in the Q&A, or maybe just get in touch with me about this design decision. That's an open question for you. All right, so that's about the composite design pattern. That's everything we need to know. And then, of course, to really understand the full details, you should also study very carefully about the previous two design attempts, in which case many details have already been discussed over there. One more question about the composite design pattern architecture, which is about a single choice principle. Okay, so now why is the composite a separate class? Right, that's really the question over here. Why is this particular composite a separate class? Okay, so now let's see why. Okay, this is why. This is because we want to satisfy the single choice principle. That's the answer. Short answer. Single choice principle. But exactly how? Let's now consider this final architecture that's very general. Okay, let's now think about it. So the composite class is really reusable by instances of the composite pattern. So in your project, there might be multiple instantiations of the composite design pattern. For each one of them, they can simply reuse the composite class. But how? Let's see exactly how. So let's talk about, first of all, on the one hand, let me just do this. On the one hand, you can think about we are simply use the equipments, right? That's actually in this particular domain for equipments. So that's our design domain. So in this case, we are simply using the composite equipments class. And now that one inherits from, you can see this particular inherits relation over here that inherits from composite. More precisely, you can think about the way we write it, it would be, we simply say composite equipments inherits the composite. I'll say comp. And then what exactly do we instantiate the G to be? Well, in this case, equipments. So I would say equipments. So accordingly, what's going to happen is the G over here is going to be replaced by equipments. And then also the G over here is also replaced by equipments accordingly, right? So that's how we reuse the generic class as we spoke about in the previous lecture. Symmetrically, so now let's talk about the other end. A similar cluster, just another instantiation for the composite design pattern. Okay, let me make it a little bit smaller, like that. Okay, so you can see the two classes. So now, what about this one here? Let me use pink. So let's say we got furniture over here, and then we also got over here, we got composite furniture, right? So the domain we talk about is furniture. And let's see, we got this particular inheritance relation over here. So now, how would we write this accordingly? So you're going to say composite furniture inherits, okay, inherits is a keyword, inherits composite. Okay, similar to before over here, but now what should be the type to be instantiated for G? So since we talk about furniture, so it's going to be furniture. furniture. So what's going to happen is, accordingly, the G is going to be instantiated by furniture. And accordingly, the G over here and the G over here will be replaced by furniture. It's a second use, or like a second reuse for the same generic class over here. And for the left-hand side over here, so now let me zoom out. For the left-hand side, for this particular inheritance relation, we are instantiating this particular generic class by equipments. And for the right-hand side, a similar design problem, a similar design solution, since we are inheriting from also the same composite class, we are really reusing it. So that means we are satisfying single choice principle. More precisely, since now we are talking about furniture, so now every generic type G is going to be replaced by furniture accordingly. Okay, so that's really the last bit of the puzzle for the architecture for the composite design pattern. Please make sure you understand about why we're doing this as a separate standing out class alone. All right, so now let's go back to the slides. I would like to now talk very quickly about how you can implement the various features in the composite pattern. Okay, so we have the equipments class. Okay, so let me just draw to you over here. So first of all, we talk about the equipments class. Okay, and then we'll talk about one basic and one composite component as well. So that's the sequence. So we got equipments, that's deferred. So now notice that the price routine over here. So at this level here, we simply don't know what the price should be for this particular equipment, which can be either basic or it can be composite or recursive. We're going to see exactly how to define that. And then for basic components, let's say for the video card, it simply inherits from equipments. So you can see what we have is video card simply inherits from equipments over here. And then we simply got, let's say this. We got some private variable unit price, and then every time you want to create a new video card, a basic component, you simply assign unit price to be the parameter. So now, how do we implement this inherited defer routine? We simply say the result should just be the unit price, which is whatever you assign that to in the constructor. Okay, that's easy. Okay, of course here I didn't really declare the make as constructor. You can do that. I'm simply omitting that. Okay. Okay, so now let's go back to go to composite. So what about the composite class over here? The composite over here. The composite would be simply a generic class, and then we got children. You can put iterable, you can put linked list, you can put list, you can put array. It's up to you. Of course, according to your programming from the interface, but not from the implementation. Maybe it's better to put maybe list rather than linked list, but just for illustration. And then for the add, it's going to take a single child of type T. So whatever T is that's instantiated, so this T will be instantiated accordingly, right? So now you can think about whenever we say children.extend, so this will be the polymorphic arguments. So as long as the T over here is a descendant class of the T over here for the member type of the linked list, you're okay, right? We're going to see one example in a moment. Okay, one exercise for you, if you like, you can try to make the composite class over here iterable. So that will make the composite class maybe more user-friendly. You can simply say across all the composite and go one composite at a time. So that could be useful for your development. I'll leave that to you, optional. Okay, let's now talk about composite equipments, basically over here. Composite equipments and also maybe cabinets, right? For the composite equipments, so now it's going to inherit from equipments, number one, and also composite of equipments, right? So now you can think about it's going to inherit from equipments and also composite of equipments. That's exactly what I said before. And notice that whenever you want to do multiple inheritance, you do not put any comma between the class names. Okay, just notice that. And then we got a constructor here, make, and also we can create empty child list. Okay, and then what about the price? How can we define the aggregation of the prices from individual components, and individual components may be themselves recursive, right? How do we do that? Let me show you the code first of all. You can think about how to define that. This shouldn't be a challenge. This should not be a challenging programming task. What we will do is we'll simply go across the children, which is basically if you go back to the composite, it's simply a list of equipments. So now every child is equipments, which can be either basic. So now the C over here is basically, remember that's simply composite of equipments. So now so that means every child is simply just equipments over here. Okay. So now how do we actually figure out the price? So now for the equipment over here, it can either be the price for basic components or it can be for the recursive components. It can be both cases, right? However, a single line like this can do. Okay, so it's simply the result is accumulated by C dot price. So here I simply say dynamic binding. I'm going to show you exactly. Dynamically, the C here can be any of the descendant classes of equipments. It can be either here, basic, or it can be here, recursive, either way. So we're going to call the correct version depending on what the dynamic type is. Okay, let's see this. All right, so now finally, let's now consider a small test and then to visualize what's happening for the composite pattern at the runtime. All right, so let's now switch to visualization. So this part of the code is exactly what's shown as the test code on your slides. And I also included also for the basic equipment, for example, video card. So that one there has its own version of the price, which will depends on the unit price. And also for the composite equipment, for example, chassis and also buses and also cabinets. So for those, the price will be defined as an aggregation of all the C dot price, right? C is simply one single child in the children list. So now let's see how we can trace the code very quickly. You got the various variables over here of the various static type. Okay, I'm gonna let you read it. So now basically here you can see we got one object card, unit price 200. So this is the object over here, card, unit price 200. And also we got this drive, unit price 500. So the drive, unit price 500 over here. And also we got a bus, which is exactly over here. And now let's say if ultimately it's going to have one child. I'm just putting it here, just preemptively. And also for chassis over here, is going to be over here. Eventually it's going to have two children. And also we got cabinets is over here. Eventually it's going to have one child. So now how do we build the composite structure? It's pretty much like how we build the nested windows in the example that we talked about previously. Let's now try to do one by one. So what about this line over here? So bus.add card. So the bus over here, the add card. So now that means its first child is now going to point to wherever card is pointing to. And what about the next one? What about chassis over here? So now it's going to add bus and also drive separately. So now here is a chassis, and then first child is going to be bus. So the first child is going to point to the bus over here, and the second child is going to point to the drive. So now second child is going to point to over here. You can see we're building the tree bottom up, right? And finally, what about the cabinets? So cabinet is going to add the chassis as the first child. So cabinets over here is going to add as the first child the chassis over here. So that's how we build a tree structure. So now ultimately the line that we really need to trace recursively is about cabinet at price. Ultimately it's going to be 700. Of course, if you look at the simple structure here, it's simply aggregating 500 and 200 for sure. But I would say we'll still try to trace this together because for your particular developments, the tree structure might be much more complicated, in which case it may not be this simple, may not be so obvious. Okay, let's try to trace it. And imagine that this is a stack. Okay, so now when we say cabinets price, we want to know if that's a recursive case, in which case we're going to put it on a stack for until it returns, right? Cabinet price. So cabinet dynamically is a composite equipment. So that means we're going to run this particular loop. Okay, so this is a cabinet, right? So cabinet dynamically is a composite equipment. So that means we're going to run this particular loop over here to go across its children. We only got one child over here, only one. So that means, so now before we can calculate the child, so now it's going to be C dot price. So C dot price. So the first child. And then the first child is simply another composite equipment over here. You can see that's another one, right? That means we are not done yet. So what I would do is I'm going to put cabinets dot children at position 1 dot price. So we are still calculating it, right? So now for that particular chassis, the first child, so now you can see we go dynamically chassis is actually composite equipments. So that means we're going to run this particular fragment of loop again. How many children do we have? How many iterations? Well, it's going to be 1 and 2. Two possible iterations. Let me try the first one. If I try the first iteration over there, it's going to be pointing to this particular bus over here. And bus is actually another recursive case. So that means we are not ready to return just yet. So let me put this in also onto the stack. So it's going to be chassis over here and the first child. The children at first and then the price, right? So that means we're going to call this C.price on that particular chassis. Okay, let me just to tell you that's the second time we're calling C.price over here. Okay, so now when we are trying to call this so we're not getting to the second child until we are done with the first one. All right. So now let's see how we're going to do it. So now now we're going to the bus. So the first child for chassis, is actually bus. So now for the bus, it only got one single child, but bus is also a composite equipment. In that case, we're also going to the composite equipment dynamically, and also we're going to run this loop the third time. So for the bus over here, so for the first child, now we are kind of meeting something that's promising, because the first child is referring to this particular equipment over here. So now this is basic, right? So that means for this particular one, you can think about we're still going to put bus.children at position 1.price. But to calculate it, it's actually quite easy, because now the first child is now referring to equipments. So now equipment is actually basic for the card, right? So now that means we're going to execute this block of code. And how do we do that? What's the unit price? You can see that when we first created the card, it's simply 200. So this one is going to return back to us 200. All right. So that means it's going to be 200, and then so that means the chassis, the first child, is also going to be 200, right? So that means this part over here is 200. So now we can go to the second iteration for the chassis, right? So if we go to the second iteration, to avoid confusion, let me just wipe this out. Okay, so this one simply just passed to the orange one, which is 200, right? So I don't want to create any duplicates. So now let's go to the second child for the chassis. The second child, luckily, is also referring to some basic equipments, right? So now let me put it here first. So you can see for the first one, for the second child, it's going to be chassis dot child at position 2 dot price. So now it's referring to this particular equipment over here. So now this one here is dynamically equipments. Dynamically is simply equipments, like a basic components. So that means we're going to go into this version of the unit price again. So what's the unit price for drive? Well, as we did before, it's simply 500. So that means this part over here is going to be 500, right? All right, so that means the second child is going to return 500. Hopefully, so far you're following. Okay, so now once we get these two pop up from the stack, so now we can go back to the very original problem over here. The price for, of course, these two, you can think about these two, 500 and 200. They will be in the two iterations of the loop for the chassis, which means they're going to be added up together, which will be 700, right? So that will be the ultimate answer that's going to be returned. So now, in order for this one to be calculated, so that one, the return value for 700 is going to be assigned to that, right? So that means ultimately, this answer over here is going to combine 200 plus 500. It's going to be 700. All right. So I'm not, hopefully this kind of trace over here is mainly to show you that what we're doing over here is nothing new. I just want to brush up your tracing skills about recursive call. It's actually quite important. Dynamically, you're going to call either this version over here for the basic equipment, or you're going to have run several iterations, in which case every iteration is going to call the price over here for another equipment, which can be dynamically either basic or recursive, right? So that's the main message I want you to get. Okay, so that's about the tracing part. And let's now conclude this lecture here about this pattern here. Okay, exactly what we just have traced. I'm going to leave that to you. Okay, you can feel free to build a more complicated structure for the computer manufacturing system and try to see how the price is going to be calculated. That's left to you as optional exercise. Let's have a summary of the composite pattern. So at the design level, we basically got two categories of the artifacts. We got base, we got recursive. We got individual versus composite. What about at the programming level? We want to build a tree, and the tree structure is definitely recursive for its hierarchy. And then at the runtime, how do we do it? So we want to allow the clients to treat the base objects and also recursive objects uniformly. For example, the price feature, right? If you look at, again, if you look at the architecture of diagram over here for the composite, you can see over here, this one cleaner. For the clients of the equipment, let me just write it out, okay? You can think about this is the clients over here. For them to really use the equipment, they simply declare the supplier. And now, whenever they want to call, they will simply say supplier.price. And the underlying structure that's built at a runtime can be arbitrarily complicated. So you can think about the clients simply got a reference to some tree structure over here. And the top level is simply some equipment over here, right? And exactly how to really build the total price for this particular tree is up to the recursive traits that I just showed to you, right? So whenever you see, say, c.price over here, so doesn't matter if this is either this case where you got a very arbitrarily complicated structure, or you simply got this. Maybe E is simply pointing to maybe just a basic component just for the video card. You will also say E.price. So that's what I meant by uniformly. So either for complicated case or for simple case, in both cases, you simply say E.price, the same. Just use the price defer routine over here, uniformly. Okay, let's go back to the slides. Okay, and then for polymorphism, you basically, both the leaves and nodes are substitutable. Basically, you can think about, given equipment, I can substitute it either by the basic or I can substitute it by the composite, right? Because all of them are simply descending classes of equipments. What about dynamic binding? So different versions of the same operations apply to individual objects and composite. So think about the price feature. So now remember the trace we just did over here. You can see for the same price feature over here, for the same price, it can either be implemented using a unit price for the basic equipment, or it can be implemented using a loop and with also the help of dynamic binding, also with recursion when you talk about composite equipment. So you got the same feature but two different versions for base case and also for recursive case. So now given E of type equipment, so you can see uniformly, you can see E.price and E.price. Now depending on what the dynamic type is for E, in the case where it's simply dynamic type of E is simply basic equipment, in that case, it's going to calculate the unit price. For example, this drive. Otherwise, if you say E.price where E is simply a composite equipment, let's say chassis, dynamically, in that case, it's going to basically going to recursively calculate all the containing equipments. Okay, so composite design pattern is actually quite an interesting pattern that will link to the tree structure that you learned in your 2011. So you may actually want to review parts about the tree operation back in your 2011. Okay, so that's about the new pattern that we introduced this week. Study the motivating problem and study about a necessary concept like a multiple inheritance, and also study about the different design attempts that will lead you ultimately to the composite design pattern. And think about the pros and cons. That's really important for your design skills.